Okay, for this mechanism, there's 1 degree of freedom. Because there's 1 degree of freedom, because I'm given one motion, I can determine the motion of everything that I want. So I can determine the velocity and acceleration of the ram, and I don't need a free body diagram. In this particular case, the velocity of the ram, well, you can think of it like this. The position of the ram is given by this distance x. So if you take a derivative of x, you'll get the velocity of this horizontal distance, which is the velocity of that slot in the ram. So x dot is going to equal the velocity of the ram. X double dot would be the acceleration of the ram. So the question really is to find the velocity and acceleration of the ram in terms of the values that are given. In this particular case, the author wants me to use these values here. I'll point out before we start that the solution manual has an error in it. So the expressions that we get are not going to be the same as what are given in the solution manual. Okay, so the first thing I'm going to do is use a vector loop. Vector loops are, as long as you use a mathematical tool, vector loops are by far the easiest thing to use when you can see the loop. In this case, the first loop that I saw was this red one that's pointed out with point O, point C, and point A. I'm going to start at point O. It makes no difference where you start, but I'm going to start at O, and I'm going to go from O to C, from C to A, and then A back to O. So you can see it down here in the equation. So this expression right here is moving me from O to C. So I move a distance of r, and then with the angle theta, I move to the right and up. That is the sines and the cosines. And then the second term here is going from point C to point A. So I'm going to go a distance s. S happens to be a variable. I don't know what it is, and so I just label it in as s. You should keep that in mind when you're doing these loops. If you don't know a particular distance or an angle, you should label it and then come back to it later. But anyway, so in this case, I'm going to, when I go from C to O, I'm going to go down. That's why this this component is a negative, and I'm going to go to the right, to the left. So this guy is also negative. So just be careful of the sines and the cosines. I think I've got everything right with that. Now I'm down there at point A, and I'm going to go from A to O, which means I'm just going to go straight up a distance d. Now if you stop and count the number of unknowns, you've got s and phi. Those are circled in blue. And you will end up with 2 equations from this first red equation. The i's on the left-hand side equal to 0, and the j's on the left-hand side will all equal 0. So you're going to end up with 2 equations for 2 unknowns. So that means you can solve for the distance s, and you can also solve for the distance phi. Turns out you can also do this with the law of sines for the triangle. So there's a little red triangle there that loop forms, and there's nothing wrong with that. The only problem is that sometimes you'll have a mechanism that's not made up of triangles, and then you're kind of doomed for what you do. But there's nothing wrong with writing those. Essentially, that's what the loops do. They're just a formal way of writing all those trig identities. So anyway, you can solve for s and phi. The problem is that x is not in that equation, so there's no way you can solve for x, which means it's not enough to just solve for s and phi. So what I need is I need a loop that will also include the distance x. So that one is this black loop that starts at, well, it doesn't matter where it starts, but I'm starting it at point A, and then it's going to go to point B, or that end of the rod up there, and then I'm going to drop it straight down a distance little l till it hits point G, and then I'm going to go from G back over to A. So when I do that, if I start at A and I go to B, I'm going to have this piece of the formula right here. So I'm going to go a distance of big L to the right and up, so that's why these numbers are positive. And then I'm going to drop straight down, that's why this guy's a negative. Down is J, and I'm going to drop down a distance of L. And then I'm going to go back to the left, that's why it's a negative, and it's left, that's I, and I'm going to distance X, and that's equal to 0 when I get back there. Okay, so if you circle the unknowns here, you don't know little l, and you don't know little x. Now, it's true that the author is telling you to put your values in little l. That doesn't make a lot of sense to me, because little l is a variable, and it's changing. So you're not really going to know what L is. You're going to know theta, you're going to know omega, but you're not going to know the distance L. It would make more sense if you knew capital L, because you build the mechanism, you know how big you made it from these two endpoints right here. So you know capital L, but little l, that's a variable. You don't really know that. So the first thing I'm going to do is solve it, a normal way, which would be to say that I know big L and not little l. So what's going to happen is when you solve this guy, you're going to have four unknowns. You're going to have S, phi, little l, and x. But you're going to have four equations. So this is solvable. Now, the next thing that you're going to do is you're going to look for the velocities. The way you find velocities is you simply take the derivative of your loop. I would suggest using Mathematica, but just to show you that it's possible to do this, the next section down in here is where I'm taking derivatives. So here, r is a constant, but theta is a variable. S is a variable, phi is a variable, L is a variable, and X is a variable. So for the red equation, I end up with this derivative here. I'm not going to read it off to you, but just check and make sure that you include the chain rule where you need it. And then this second term here, the S term, this guy, that's basically a product. And so I'm using a product formula. So here's the first term of the product derivative formula, and here's the second piece of it. Okay, so just don't forget that you have those two pieces, and that's equal to 0. Notice that the dj disappears because d is constant, so is j. So now for the black equation, the variables there are phi, L, and x, and so you end up with this derivative right here. And then just to show you how you pull equations off, I'm going to pull off the two equations, the two velocity red equations. So I'm looking in the red velocity equation, and I'm looking for all of the i's. So here's an I term. It corresponds with this one. Here's another I term over here, which corresponds to this one. And then the last I term is this piece right here, which corresponds to this one. And then for the other equation, you pull off the j's. So this term right here is, if you look at the red velocity equation, pull off the j's, you get this one. Then you also pull off 2 for the black equation, which are right here. So that's going to give you 4 unknowns. You never solve the velocity equation for the undotted terms. So for example, you never take these equations like this. You would never take these equations and try to solve for phi. You just don't do it. You solve for phi dot and x dot and L dot. Same thing up here. You don't try to solve this for S. You would only solve for the dots. If you want the undotted terms, you go back to the undotted equations, these guys, and you'll pull off the i's equal to 0, the j's equal to 0. So here you'll get 4 equations, and there will be 4 undotted terms that you would then solve for. That would be S, phi, L, and X. So whenever you need the undotted ones, you solve undotted equations. When you want the dotted terms, you solve for the single dot equations for the dots. And then for acceleration, you're going to take another derivative. I wouldn't do it by hand. And then you're going to solve for the double dot terms that you'll find in there. And there will be 4 of them. Everything will work out fine. Okay, so what I'm going to do is pause it now, and I'm going to pull up Mathematica and show how to solve this with Mathematica. Okay, so here is a Mathematica file that I use to solve this thing. This section right in here is just a piece of code that allows me to use I, J, K for vectors. This one here is just to try to help make typing simple. All I'm doing is saying theta is a function of time, phi is a function of time, L and X. So just some convenient ways of typing things. ST is the sine of theta, just so that, just for typing. Okay, so here's the first loop equation that you would write. And if you look back on the notes, that's exactly the same thing. So it's, R sine theta I plus cosine theta J, etc. The only thing to watch out for is if you're going to use this these definitions from up here, just make sure that when you set it equal to 0, you make it a vector. So 0I, you could say 0j, 0 times k, whatever, but you have to put that I in there. Otherwise, what you're looking for is I equal, the I is 0, the j is 0, and the k is 0. If you just say 0 with nothing else, you won't get all of those. Okay, and then all I do is I take a derivative and a second derivative. And if you want to, you can match this up against the first derivative that I had by hand, and you'll see that I did it right. It's a little awkward to look at these things, but if you notice the first comma, for example, this term right here is the I part. Okay, and then this between here and the second comma, that's the J part, and then the K part is 0, as you'd expect. It's only 2 dimensions. And same thing with the others. So they're all kind of embedded in there. It's kind of hard to spot them, but they're in there. Okay, and then this one here, this last one, that's the acceleration. And that's for sure the one you don't want to do by hand. It's just too many terms. Okay, so there's my equations, and then here's how you solve them. This guy right here is just that a function that I wrote. You don't have to use it. It just pulls off the I and sets them equal to, the i's on the left equal to the i's on the right, j's and j's, k and k, and then solves them. But you can do that without all this stuff. Now, because you're solving for an angle, this phi is an angle, because you're solving for the angle, Mathematica is very picky about it, and it tries to give you all of the possible angles. Well, if you look at this guy right here, it's adding 2 pi times an integer. So 2 pi times 0, 2 pi times 1, 2 pi, well, that's all they're doing is adding 360 degrees. You have an infinite number of answers. The other thing is that if you notice, there's 2 infinite number of answers. So for example, here, here's one of them, and it shows that little l is a negative number. And then in the second answer, which begins right here, okay, from here down, that's the second answer. If you notice here, the little l is a positive number. So I say that what you want is you want the second answer, not the first answer. So what I'm going to do is I'm just going to say, okay, answer is the solution. There's 2 of them there. I'm going to tell Mathematica which one that I want. So that's this notation right here. So I'm going to take the answer, and I want the second one. So it's got a little cryptic, but that's the way you do it. And then this thing right here says I also want you to put a C1 of 0 in here. So I want you to put a 0 in here for the C1 and give me that answer. So this is the answer that I'm looking for right here. So you can see, given the variables that I have, I've got an angle, I've got R, I've got D, all of these things. I can find the value of S, I can find L, I can find X, and I can find phi. Okay, now they look complicated. Mostly, it's things like this where Mathematica insists on keeping like this arctangent. If you notice, the denominators are the same. So we would just drop those, right? But it's going to keep it because it doesn't know that this d squared, r squared, etc., it doesn't know that that's not 0. So it's really trying to make sure that you get all the correct answers. Anyway, so that's the position answer. And now here are my velocities. So this is the derivative answer and the double derivative answer. And I do basically the same thing. I'm going to solve the dotted equation, the dotted loop equations. Up here, I solved for S, phi, L, and X. Down here, I'm going to solve for S dot, phi dot, L dot, and X dot. And then for the acceleration equation, I'm going to solve for the S double dot, the P double dot, or phi double dot, L double dot, and X double dot. Okay, and these are much easier to solve because they're linear equations, basically. And you can see, and now the one that I'm looking for is this one right here. This is going to be X dot. That's the velocity of that ram. And then the acceleration is this piece right here. That's the acceleration of the ram. And if you notice, it's for the velocity, it has undotted terms that are not known for this equation. For example, it doesn't know what phi is, right? Where am I going to get phi? Well, I've got phi up here at the undotted equation. So there's phi. So what you do is everywhere you see a phi, you're going to stick this in. Now, if you were doing this, in the real world, and you were doing it on a continuous basis, you would come in here and you plug numbers D and R and theta, and you get the phi, the X, the L, and the S. So you get those four numbers, and then you'd put them in down here. You wouldn't try to do the algebra, but in order to punch it into the solution, you need the algebra. So now you're going to have to kind of fight through the algebra if you really want to get there. Okay, so the velocity of the ram is the X dot term, and so I'm putting in the algebra. So what I'm doing is I'm telling Mathematica to take the first solution for the X dot, right? So I'm taking the X dot, and I want the first answer, and I want just the X tick, right? So I'm taking X tick using the answer here. So basically, it's going to pull off the right-hand side of that. The velocity of ram, and then I'm just going to simplify it. Now, what I'm doing here, if you remember, this is the solution that has phi and X and L in it. So what I'm doing is the first one, I'm saying I want you to just pull off that first answer. So it did. Right? You match that up. Then what it's going to do is it's going to take this answer here for the phi, S, etc. See, you don't know the S, you don't know the phi. So then it takes the answer for the S and the phi and it shoves it in, and you get this big ugly mess right here. Let's see, velocity, that would be, I think it's this piece right here. A little bit longer because you've taken the algebra of the phi and the S and everything, and you put them in here. Now, if you look at this one that I've circled here, the only things that are in here are the constants. You know the length L, you know R, you know D, for example, you know the theta, you know where the position is, and so these are all numbers that you're going to know, and you can just put those in and get a number. Same thing with the acceleration; it's just a lot uglier. It's just much more complicated. Just to show you that it works, I'm going to put in some numbers. So I'm just going to make up some numbers. So I make up a number for D, R, L, put theta at 30 degrees, and theta, omega, is 3, and I think the book said it was constant, so that's 0. And then all I do is I say, okay, plug it into the undotted solution for the velocity and for the acceleration, just to show you that if you know these numbers, you get numbers out for this guy. Okay. I shouldn't do that. Okay. So anyway, so you put the numbers into this, and sure enough, you get a number for S, you get a number for L, a number for X, a number for phi, and this is in radians, right? And then you put it into the velocity and the acceleration, so you get the numbers for that. Okay. Now, all right. So what the book wants you to do is not have an answer that includes big L. It wants the little l. I'm calling it EL just to make sure that you don't think it's a 1. Okay. So anyway, it's just basically the same thing. So here we go. Here's the loop equation that we had before. You can look back, no big deal. The only thing that's different now is before I solved for EL, right? That was the lowercase l, right? And now instead of solving for lowercase l, I'm going to solve for big L. And that way it leaves the little l in, takes out the big L. And so you can see that, sure enough, here it is. Here's the first solution. Let's see, the second solution for x. Here we go. Here's the second solution for x. You want the second solution, right? Because the first answer, big L, is a negative number. Down here, big L is a positive number. So you definitely want the second solution here. I'll draw a line here. So you definitely want the second solution like you did before. And notice that now the x is, in terms of the r, the l, theta, d, just like it was before. Okay. Well, before we had big L, not little l, but that's that's what the author wants, so that's what we'll do. Okay. So then I'm going to pull off the second answer and use C1 as 0, just like I did before. This is no big deal, right? It's no different. So this is really the position of the RAM. Okay, and so here's the derivative answer using EL instead of capital L. And I'm basically doing the same thing I did before. I solve for phi dot, s dot, l dot, x dot, because according to the author, I do not want the velocity to have l dot in it. So I'm going to get rid of l dot. Okay. And here's the solution. And then the acceleration is the same. You're going to solve the double dot equation for the double dot terms, right? Just like before. And the acceleration equation is down here. It's big and ugly. It's no point even looking at it because there's nothing important there. But anyway, so here's the x dot. This is the velocity of the ramp. Now, what it has in there is it still has this s, just like I had. So if you want to fight through the algebra to be able to punch it in, you're going to have to, right? It also has this phi right here. And so what you do is you got to get rid of those guys. So what do? You take the velocity of the RAM, okay, and I'm just going to pull off the first term, and I'm substituting in the answer for the thing. So here is the x, and then what I'm going to do is right here I'm going to take the velocity of the RAM, and I'm going to substitute in the answer. This is the undotted answers. Those have phis and s's, etc. And this is what you end up with, this big mess down here. Let's see, this is the velocity. One of them is velocity, I forget where it ends. Let's see, that's the position. Where is the velocity? Well, anyway, it's a big mess. But if you notice down here, there's no s's, right? Up here there were s's and phis, and now by substituting that in, you've gotten rid of all of the s's and the phis, and the only thing that's left down here are the things that the author wants you to have in your answer. To show you that, because it's difficult to spot it, I realize, to show you that, I'm going to pick up some numbers. I'd pull them out of the sky. They're basically the same as they were before. Here's the difference. Before, I told you what big L was. This time I have to tell you what little l is, because that's what the author says. You're going to put your answer in terms of these numbers. So when you put in the velocity of the RAM using these numbers, what do you get? You get a number, right? What do you get when you put these numbers into it? You get a number, okay? Now, the solution in the solution manual is wrong. Let me show you what the solution manual does. The solution manual comes in and it uses the law of cosines and the definition of a tangent of an angle, and it basically finds the distance x, which is okay. And I told you when we started, you don't have to use vector loops if you can find these triangles and that sort of thing. But you have to be careful, right? And not everything's going to be a triangle. But anyway, so the solution manual gets this, and I don't disagree with this. Okay, this is the correct answer for the distance x. But then what happens is, in order to find the velocity, the author wants to, or whoever it was that did the solution manual, takes a derivative of this. I don't have a problem with that. When you take the derivative, they treat the L as a constant. And so what happens is if you do that, just like I'm doing here, you tell Mathematica, hey, take the solution, take the derivative for me. And so what happens is down here, right, here's the mistake. So here's when you take the derivative treating L as a constant, this is what you end up with, which is a nice little, simple, compared to what I'm getting up here, oh my goodness. So this one is a simple little formula. The problem is that L is not a constant. L is a variable. If you look at it real close, L changes. So, the true derivative would be this, right? So all I've done is I've modified the L, and I've told Mathematica that L is a variable, along with the theta. Then when you take a derivative, you end up with this. And if you notice, this is a lot worse than this one. This is the answer that they're expecting you to punch into the mastery to get the solution, but that's not right because they didn't take the derivative properly. And then when you take the second derivative, it's even worse because of the L being a variable. So that's the problem with that. Other than that one constant, everything was okay. All right. So anyway, that's the end of that one.